Hello everyone, in this lecture we are going to explore two groups of chemical compound. The first one is ether. So when we talk about ether is this group of compound that the oxygen will form two sigma bond with two sp3 carbons. So these two alkyl group can be the same or different. It really doesn't matter. This is ether. So when we talk about ether can be symmetric. When these R1 and R2 groups, they are the same. Then, for example, this is very common solvent that is called diethyl ether. So when they have the exact symmetric, that is diethyl ether, to have two ethyl group on the oxygen. And it can also be asymmetric. For example, if we have one side you have acyl group, the other side you have isopropyl group. So for this one, if we name it, we can call it isopropyl. So basically you tell isopropyl ether, tell what is the R1 and R2 groups. And this is a common name. So common name basically is the name of the substituent or substituents if you have different ones plus ether. So this is a common name of ether. And if we're talking about the IUPAC naming, it will have a little different way to name it. IUPAC systematic naming. So if we are looking at the ether now, what we will do here is we will treat one side, the alkyl group with oxygen, that as a substituent. So that is a alkoxy group. And then the other side basically is an alkane, right? Alkane. So basically the alkane with the alkoxy group. Now let's look at one example. If we have this molecule right here, this is a ether, and we have this molecule right here. So first of all, use the longest carbon chain as alkane. So that longest one will be 1, 2, 3, 4, 5. And then we will number it as a number rule for the parent chain to give the substituent the lowest locant as possible. So we'll start from 1, 2, 3, 4, 5. And for the substituent, it's on the carbon 2, and it have two carbons here, 1 and 2, two carbons here. So two carbons, if we have acyl group, right, that is two carbons, you have two carbons. This is two carbons, 1 and 2. We can acyl. So if we add one oxygen here as alkoxy group, so we call it azoxy. So OXY as a substituent for the alkoxy group. So that is azoxy group. And we have two azoxy. And we have 5 carbon in the parent chain, so it's a pentane. And we also notice that there is a sterol center right here. So for this sterol center is 1 and 2 and 3 and 4 is the hydrogen. So hydrogen pointing away from us, so that is R. Don't forget your sterol chemistry for the naming. So this is one example. Another example, let's look at this one. So if we have this molecule right here, we have chlorine. Okay, that chlorine, and we have O. So now what we treated here is, because the ring has the most number of carbons, so the ring now is treated as the parent chain. So this ring is a parent chain right here. So that is cyclopentane. And now what we're going to do is we're going to label it the number, and I'll always give the lowest number to the substituent as possible. So in this case, we will have it's 1, 2, 3, 4, 5. So you may think about when we label the ring for the alcohol, if OH group on the alcohol, the OH gets the first. But if we have alkoxy group, that group will not always get the first unless that will give you the lowest number possible for the substituent. We will just treat alkoxy group as a very normal substituent. Okay, so in this way, what we have here, again, we have a stereo center right here. So we have 1 and then say 2 and 3. So 1, 2, 3. This also gives us R. So we have R, and now we have 1, 1. That is dichloro, right? And 3. Again, this is the ethoxy group as well. And we have cyclopentane. Okay. So this is the naming for the ether. You should know both the common name, how to name it, and the IUPAC naming. Based on the name, you should be able to draw out the ether also. So the next thing we're going to cover is the structure, and based on the structure of the ether, what is the physical property of ether? So ether is a great solvent for the organic synthesis lab. It's just because it is low boiling point, for example, because remember that it does not have the hydrogen bonding, so it always have a lower boiling point than alcohols. Because alcohol, you will have the hydrogen bonding. The stronger intermolecular forces give you the higher boiling point. And usually it is immiscible with water. So if you do the extraction, it will separate to 2 layers. And this word immiscible, that is usually talk about 2 liquid, 2 solvents that cannot mix together. Miscible means they can mix together. And the reason why it makes to a great solvent because that it have a low boiling point that is very easy to remove. And also ether it's not very reactive towards a lot of compounds, so that makes it a really good solvent for the organic synthesis. And also think about, right, you have this oxygen. This is a polar molecule. It's have this dipoles, make it a polar molecule. That means it can dissolve a lot of organic molecules. A great solvent. For example, the very common solvent where I see it one time, this is diethyl ether. This thing smell really strong. The boiling point about 40 degrees Celsius, and you can smell it in the lab if you are using it, and you do not want to inhale this a lot because that will make you very dizzy. And another one, for example, this is a really good solvent as well. It's called 1,4-dioxane, right? It's kind of, this is a name. And another one is called THF. So T is stand for the short term tetra, and H is hydro. That means it have hydrogens and furan. So this is THF is a good solvent as well. So where that comes from? So if you are only talking about furan is look like this. So you have these 2 pi bond, and then you basically put add hydrogen to the pi bond, and then add 4 hydrogens, give you the THF, tetrahydrofuran. That is the physical properties of the ether. And another thing that your textbook mentioned about is called crown ether. Oh, what's going on here? Crown ether. So it's still ethers. It's just it have a lot of oxygen, for example. And then when you look at this, the structure of this crown ethers, it look like a crown. That's where the name comes from. And crown ether is a really great organic solvent that can help the cations dissolve in the solvent. Why is that? Remember, all this oxygen have these lone pairs, right? And for example, you have some cations that positive charge, the exit here is just some cations. It will kind of wrap around these cations to help it dissolve in the organic solvent. So how to prepare ether? There are several ways to prepare ether. So the first we are going to look at if we are prepared from alcohol, and that is so-called Williamson ether synthesis. So this is a specific type of reaction that developed by this guy. So make sure that this is the first I can kind of name the reactions we learn here. Williamson ether synthesis. So the whole idea here is if you start with a alcohol and you throw in a strong base, and then after that you throw in a alkyl halide, what you will have here is you form the ether. Okay, so for example, if we are looking at, we start from the ethanol, and we have sodium hydride. Sodium hydride is strong base. So what happened here, you already know, it will grab this hydrogen right here and give us a isoxide. And we know that isoxide is a very strong nucleophile, great nucleophile. So if we have a great nucleophile, if we do have a, especially in this case, it's a primary alkyl halide. So what happened here is it will have an SN2 reaction going on here. It's attack this carbon here and kick off the leaving group at the same time. So what we are generating here is this ether. 1, 2, 3, 4. Always count your carbon. 1, 2, 3, 4. So 1, 2, 3, 4. This is our butyl, right? Butyl. Following alphabetical order, butyl, and you have ethyl and ether. Ethyl ether. So butyl ethyl ether. That is the product. So you notice that here is primary carbon, and also here is a primary carbon. Okay, so this follows a SN2 reaction mechanism. And another example, if we start with, so this is called phenol, right? PHEN. No. Okay, this is not a, theoretically it's not alcohol as a definition, but it has this OH group. So phenol, we know that the pKa is much higher than the pKa is much lower, the acidity is much higher than the alcohol. So if we introduce the hydride, this is from sodium hydride, and it will grab this hydrogen and break the hydrogen oxygen bond. So what you have here is this. And this one also contact the primary alkyl halide as the SN2 reaction mechanism. So attack here and kick off this iodide, for example. So what you will have, the product here is, okay, you have this oxygen and then introduce this acyl group. Okay, so you have phenyl. This is phenyl group, right? PHENYL, phenyl group. And you have ethyl, so ethyl goes first, ethyl ether. If we are looking at the Williamson ether synthesis, we noted that because it's an SN2 reaction, after the first step, the deprotonate the alcohol to a strong nucleophile, then attack a primary alkyl halide. That is when the SN2 reaction would happen. So Williamson ether synthesis, the alkyl halide needs to be primary alkyl halide. I think that is when the best reaction happened here. So think about if this alkyl halide is a secondary alkyl halide. So what happened here is you create a strong nucleophile, but most of the time it's also a strong base. So the E2 reaction will be dominant for the secondary alkyl halide. And if this alkyl halide is a tertiary alkyl halide, the problem here is you will not even have SN2 reaction mechanism. E2 reaction will be the major reaction for it. So here, the alkyl halide for the Williamson ether synthesis needs to be the primary alkyl halide. The second way that we can use to prepare the ether is through the addition reactions, addition to the pi bond, addition to the alkene pi bond. And we know alkene has one pi bond. So for example, if you start with this alkene, the reason why I label this R group is that we want to look at the stereochemistry here. So if you have reaction first, if you introduce this to the mercury acetate, we see this before, and instead of water, right, when we talk about prepare of our alcohol, we introduce water. If we use the alcohol instead of water in this case, R4 is the fourth alkyl group that we introduce here. And the second step, we use the sodium boron hydride, which is a great reducing agent. That what we will have here is we will add the OR4 at the more substituted carbon, okay, and we'll leave R3 alone. So here, probably this will be a carcinoid. It really depends on what is R1 and R2 group. So you need to think about stereochemistry here when you learn this addition reaction to the alkene. So in this case, we find a way to actually make the tertiary carbon, right, connect to the oxygen. Williamson ether synthesis, we can only add the primary carbon to the oxygen. So what happened here is we basically added the OR4, the alkoxy group, and hydrogen added, and hydrogen is at less substituted carbon. That's called Markov-Nikov addition. We are not going to talk about here. And for example, let's look at this. If we have this alkene here, and we introduce, okay, step 1, we introduce the mercury acetate, and we have ethanol, and step 2, we have sodium boron hydride. So what we basically here is we have this here and OSO, and then the other side we add that hydrogen. So I'm going to actually highlight this hydrogen is added, and this ethoxy group is added. Okay. So that is our product. Again, we need to actually think about the stereochemistry here. And for this one, basically we'll have a squiggly line. So you either have it, basically you have a pair of enantiomer in this case. Next, we are going to focus on the reaction of ether. As I said earlier, ether is a good solvent. That means that ether is not very reactive, but there are still some reactions that ether can undergo. The first reaction we are going to look at is acid cleavage. Okay, So basically it sounds like there need to be some acid involved. Let's look at it. So this is isopropyl ether. And what we will throw in here is excess amount of SHX. So the X can be bromine or iodine. Nothing else. It cannot be chlorine. That is come from the how this reaction mechanism goes. And what we will have here is we will basically produce two alkyl halide at the end plus water. Okay, so let's look at the reaction mechanism and why bromide and iodide will only work in this reaction. So for example, we start with our ether, okay, and the first step, let's just use the bromide. So what happened here is proton transfer, right? So what we have is, now we have the hydrogen right here and make it the oxygen positive, oxygen ion. And also we have this bromide, okay? And the bromide is a good nucleophile, right? Now if we look at this step, we have the positive charge on the oxygen, make it a good leaving group, right? Either this side or this side, and we have a strong nucleophile. Then next, what do you think would happen here? You have a strong nucleophile, you have a good leaving group, SN2 reaction will take place. And the first question is which carbon it will attack, which alpha carbon it will attack. In general, it will attack the less sterically hindered carbon. So in this case, probably the carbon on the right actually will be attacked more easily than the other one. Even both are actually primary carbon. And we'll kick off the leaving group. So what happened here now, you will have the isobromide as one product, and now you will have 1, 2, 3 OH propanol as the leaving group and also as the product intermediate in this case. And then you have another HBr, right? And what happened? It's keep going. It will grab this hydrogen, and now what you have now is, again, you create not 1, 2, 3. Okay. You have a good leaving group as water, and you have your bromide, another bromide, and this bromide now kicks in SN2 reaction again, and that will give you the propyl bromide and the water. That is where this water comes from. So basically this is our product, right? We have propyl bromide and isobromide and water. And for the acid cleavage of the ether, sometimes it will not undergo the SN2 reaction. Instead, it will undergo the SN1 reaction when the carbon that connects to the oxygen is more substituted. For example, if we can have this third butyl iso ether, and if we introduce, actually just need two equivalent of HBr, right? Let's put a heating here. So what we will get here is you will have third butyl bromide, you will have methyl bromide. So let's see how we draw this. CH3 and bromide, okay, and water. So if we are looking at this reaction, we start with our ether. Very similar, you have HBr, okay, let's grab this hydrogen, and what you will have here is a good leaving group now, and with Br. So the first question is which one take it first? SN2 reaction faster, right? Because you have to wait for the leaving group to leave for the SN1 reaction. So the strong nucleophile immediately attack here, right? Less sterically hindered and kick off this leaving group. So what we have now is we have terbutanol plus we have the methyl bromide. Okay, and then we have HBr, and this attack again. What you will have now is tributyl connect to water, which is a good leaving group. But at this moment, because it's a tertiary carbon, it will not undergo the SN1 reaction anymore. SN2 reaction anymore. It will undergo the SN1. So the good leaving group leaves. You will have your tertiary carbon. I should now draw it like this. So let's draw it prettier. So you will have your tertiary carbon, which is very stable, and then your bromide comes in. So this bromide comes in from either side. So if it is stereocentric, you need to think about stereochemistry here. That will give you the tert-butyl bromide through the SN1 reaction mechanism here. Okay. Now let's look at another example here. If we have the phenyl group, we already know how to synthesize this. If we have this phenyl oxo ether, okay, and if we introduce HI, if we just put HI over the arrow, that means it's excess. You can also say excess amount, okay. And what we will have here is you will have phenol that is produced and are connect to the iodide, alkyl iodide. Why is that? Because remember that this is a sp2 carbon, okay, that will not undergo any substitution reaction, either the SN1 reaction or SN2 reaction. It's not happening. So there will not be the second substitution reaction happen. So this will be your product here. Even you have excess amount of HI, the halogen acid. Another reaction of the ether I just want to mention about here is called auto-oxidation. So this is actually a radical reaction. So that also explains why we always keep the diethyl ether sealed really good and in a cold condition. So what happened here is, for example, this is our diethyl ether. It will react with oxygen in the air, and we basically insert this oxygen to here. So make it a hydroperoxide. And you do not need to know this reaction mechanism at this moment. You just know, okay, ether also can undergo the auto-oxidation. That is why when you take care of the diethyl ether in the lab. Now we are going to look at another group of compound that is more interesting than ether because it have much more reactive. That is called epoxide. So epoxide, also this oxygen will connect to sp3 carbons. The difference here is it will form a three-membered ring. And that degree of unsaturation at least will be 1, right? Because you have this ring formed here. And you'll have this R group. This R group can be the hydrogens. It can be alkyl groups. Can be the same alkyl group. Can be different alkyl groups. So the reason why it's more reactive because when we talk about ring string, right, the three-member ring, the ring angle is like 60 degrees. That is very far away, very different from sp3 orbital. That is 109.5 degrees. So there are a lot of ring strengths that this ring is very unstable, make epoxide very, very reactive. And for epoxide, we always call it epoxide, and official name actually is called oxyring. Okay, oxyring, you have an oxygen and ANE, that basically give you the idea. It's kind of like a alkane, right? Alkane, but add oxygen in there. So if we are looking at the naming, systematic naming here, there are two ways to name it. So way 1 one way or another way. Way 1, if we are looking at, for example, this molecule, the epoxide right here, I will put it, the SO on here, and I have 2 methyl. So the way 1, we will treat it, the whole name, the parent chain is oxyring. Okay, we will use oxyring and the parent chain. That means we will treat all this part right here as a substituent. If we call substituent, it's called epoxy, okay, as a substituent. Okay, so in that way, what we'll look for is the longest carbon chain as the parent chain. And what we'll look at here is we'll have 1 and 2 and 3 and 4 and 5. So it's pentane, but we are not going to call it oxypentane. It's just oxyring. And what we want to do here is we want to indicate where is this epoxy located. So on this parent chain, epoxy located as 2, 3. So epoxy and then oxyring. Okay, that's basically give us an idea where is the epoxy, and the thing is called oxyring. And then we'll put the other substituent on it. And we also notice that there is a chiral center, and this chiral center, let's see, so you have 1, right? You have this 2 and 3 and 4. So you have R right here. So put it in there, R. And we have on carbon 3, we have 3 SO. We have on 2, you have 1 methyl. On 4, you have another methyl, so 2,4 dimethyl. 2,3 epoxyring. And another way to name this compound, I will draw it one more time right here, is to use the ring, epoxy ring, as the parent chain. And when we label it, we will label as 1, and then where goes 2. So it goes based on these 2 carbons, they have the same degree of substitution. Then we goes to the alphabetical order. You have ethyl group on the left side, so this will go to 2 and 3. Okay, and for this one, we simply just call it oxyring. Okay, the difference here is you incorporate the epoxy as substituent to name the oxyring. And for this one, oxyring is the parent chain. And now, what we are going to do is, so R, we will say 2 SO, right? On 2, you have a SO, and then on 2, you also have isopropyl. And then we have 3 dimethyl. So basically, we just methyl. We basically put the other substituent on. So that is the second way you can name an epoxide. Now we know how to name epoxide. The next what we are going to look at is how to prepare the epoxide. Okay, preparation of epoxide. And the first reaction is another addition reaction, and addition to alkenes. And you will learn this reaction later, so I'm not going to talk about reaction mechanism right here. So for example, if you start with this alkene, and you notice that these 2 carbons on the pi bond, they are different degree of unsaturation. And what we introduce here is so-called peroxy acid. Okay, it's called peroxy acid. This is just a general way to write a peroxy acid. Okay, and what you will have here is you will make a epoxide. So this epoxide, this oxygen, will add it from the same side. You notice that the way I draw this molecule, so they push the methyl group back, and also it will also form the enantiomer. So these two carbon oxygen bond can also be pointing away from you and push the methyl towards you. This is a kind of addition, basically called syn addition, right? You add this carbon oxygen bond both point at the same direction. That is syn addition. And for the addition to alkene through the peroxy acid, it has a stereo chemistry consideration, specifically stereospecificity. For example, if we start with this alkene that these two substituent is on the same side, so we call it cis, right? Now cis, if we introduce the peroxy acid, for example, this one is called MCPBA. So what is MCPBA? MCPBA is this molecule right here. So basically, you have a chlorine on here, that is the C, and you have a peroxy acid, OH, and M indicate the relative position. This is called meta position. So this is meta. This will give you the position, and the chloro is C, peroxy is P, benzoic acid. MCPBA, you will start to hear this a lot. MCPBA. Okay, so basically that peroxy acid. So what happened here is if you start with the cis alkene, and when you add the oxygen here, you have your epoxide, and these two group, the R group, can be the same R or different R, it doesn't matter, they will push to the same direction. And if you start with the trans alkene, if you introduce MCPBA, and if you form urine, this 2R will push to the opposite side of the ring or the paper plane. And if the R1 and R2, for example, I'm going to change this R1 and R2, they are different, then what you will have here is you will have the enantiomer of this molecule as well. So R1 now can be also being back, and R2 is pushing to the front. So that is the stereospecificity of the addition to alkene to make the epoxide. And another reaction to make the epoxide also is first step is also addition to the alkene, and then we will go through a SN2 reaction mechanism. For example, if we start with this alkene, the step 1 will introduce bromine and water. So this reaction is called halohydrin formation. Halohydrin formation. You will learn this in the alkene chemistry. And what you have here now is basically add one OH group from water, and then the bromide from the bromine, and also you will have the enantiomer in this case. That OH group can also be pushed to the back, and you notice that the OH and Br is added on the opposite side of the ring. So that is the anti-addition. It's anti-addition. And then the next step, you will introduce a strong base, and then what happens here is you will form this epoxide. So I'm now going to talk about the reaction mechanism of the halohydrin formation. You will learn it in the alkene chemistry. What I want to talk about is how we get the second step, the reaction mechanism of second step. Basically, it's an intramolecular SN2 reaction mechanism. So what happened here is I'm just going to take one of this enantiomer, and you have OH and Br right here, and you introduce a strong base. So this strong base, sodium hydroxide, will actually deprotonate this OH group. And what we have here is we'll have the oxygen now have this negative charge, and we have this good leaving group. So the next, the strong nucleophile comes in from front and kick the bromine away, and that gives us the epoxide. Okay, and you may have questions. Why is not a E2 reaction since you have this strong base and then you have this good leaving group? My explanation here is, let's draw out the chair conformation. So we have this bromine to the axial position to be reactive, and at the same time we'll have this oxygen carry the negative charge in the, okay, that is too much too much. Okay, carry this negative charge. Okay, so why is now E2? Think about if E2 reaction, you have the hydrogen right here in order to be eliminated for the E2 reaction. This oxygen is too far away to grab that hydrogen to form the E2 reaction. In other words, the activation energy of that reaction is so high that the E2 reaction will not be favored. And for this nucleophile here is very close to this carbon, so it's just come down to attack this carbon and at the same time kick this off. And now we will have our epoxide as the major product, SN2 reaction mechanism wins here. When we talk about epoxide, that three membrane is very unstable because of the ring strain. So one famous reaction of epoxide is to break down that ring strain by opening the ring. So this type of reaction called the ring opening reaction. What we are looking at here are two different types. The first type is if we introduce a strong nucleophile, then what will happen? For example, we have this starting material, this epoxide, with two carbons that have different degree of substitution, and we introduce sodium hydroxide as a strong nucleophile, and then we introduce water, which is a proton source. I will explain that in a little bit. That what we will have here now is we will have a diol, and the chirality of this carbon stereochemistry is now changing here. So this is a diol, right? It have two OH group. So this is R12 propane. You have three carbons here, and propane diol. So this is a strong nucleophile. So any strong nucleophile will work here. It has to be a strong nucleophile. So another example will be if you have this epoxide and we introduce a nucleophile. I will just in general put it here. If we have a strong nucleophile and then we give a proton source, which is water, what we will have is this strong nucleophile is going to be substituted in here. Open the ring, and what we will have here is OH right here, and we will have the nucleophile. You notice that stereochemistry change on this carbon while the nucleophile attack. Okay, that tells us something. That is probably an SN2 reaction mechanism. And the key point here is we need to think about regioselectivity, which carbon the strong nucleophile will attack. So the strong nucleophile will always attack the less hindered carbon. What that means? That means less substituted. And also, we notice that if that carbon that being attacked is a center, stereo center, then that stereo center will have inverted stereo configuration. Now I'm going to give you another example here. So we start with this crazy looking epoxide. 1, 2, 3, 4, okay, for plenty. Butyl group, and we have this acyl group on this side, okay. And I will say introduce, maybe first we introduce the cyanide group, which is strong nucleophile weak base, and second water. So what happened here is, let's look at the reaction mechanism here. So if you have this strong nucleophile counting to the less substituted, less hindered carbon, right, electrophilic center, and at the same time this kicks off so the leaving group. So you may ask, oxygen is not good leaving group, why here leaves? Is that because the ring strength is so strong that it can act here as a good leaving group? But normally when we talk about alkyl halide, right, oxygen itself is not a good leaving group. So it forms, let's just follow my arrow here. So it forms that it will form this oxygen negative charge. Now you do not change the stereochemistry at this carbon. However, because it's SN2, so the CN will back attack, right? This is the bond that leaving, so the CN will be in the paper plane but on the opposite side, so it's on stick still but pointing kind of down, right? And you will have your acyl group. And then the second step we have here, we have this water as a proton source. I'm going to change another color and give the proton to the oxygen. That gives us our product. This is a crazy looking one. 1, 2, 3, okay. And OH and SO and the CN and your SO. That is our product. And you notice that here, this carbon, the stereo center, the carbon configuration is the opposite now. Regenerate. So the second type of ring opening reaction for the epoxide is called acid catalyzed. Ring opening reaction. So basically, you introduce the acid as the catalyst. You use it and then you reform it. So the acid is used as a catalytic amount. So for example, if we have this epoxide, if we introduce HX, it's acid. So basically what you have here is you will have one side you will have the halide, the other side have an OH group. So usually when you write this reaction, you will have H plus in a bracket. What does that mean? That means this is acid catalyst. And it's at catalytic amount. It doesn't need a lot, just need to have a little bit to kickstart the reaction, and will regenerate through the reaction. And in this case, what we have here is, instead of introduce the X group, we will have OX, the OH group, actually from the water. And if we introduce the acid as catalyst and we have a alcohol, for example, then what we will introduce here is OR group, right? Epoxide group, and then OH group. So your question might be, what's happening here? Let's look at the reaction mechanism. So if we start with our epoxide, so this one is called ethylene epoxide. Ethylene. This is a common name, epoxide. So why is that? Okay, this is ethylene, so it's CH2. CH2, this is called ethylene. And then you put oxygen onto the double bond epoxide, ethylene epoxide. Ethylene basically give you 2 carbons there. So if you have the hydrogen, the reason why I write as a hydronium, because proton usually will not stay by itself if it's in water, right? It forms the hydronium, and it will have a proton transfer that will give you this intermediate, which have the positive charge on this oxygen. What does that mean? That means actually here now is a good living group now, right? It's just like water. Instead of water's OH2, you have one H on oxygen, the other is a basic carbon. And then if you have water in this reaction, the water now will act as a nucleophile. For this case, because this is a secondary carbon, so water comes in, okay, and kicks off this. So that is kind of like eccentric reaction again, right? So what you have here, kick that off, OH is right there, and you will have water now adding to here, so you will have a positive charge. And now that is why the catalytic amount of acid, you regenerate this acid to form your product. This product is a diol, right? And you have your acid regenerated. One of the complicated part of acid catalyzed ring opening of epoxide is when you think about stereochemistry and regiochemistry. For example, if we have a epoxide, okay, that form this intermediate, this epoxide, one carbon is primary carbon, the other have one of the methyl group. And what happened here is, in this case, steric effect wins. What that means? That means if you have this weak nucleophile, for example, methanol comes in, okay, that will actually attack the less sterically hindered carbon. Okay, and that will give you the product here. I'm not going to draw the full reaction mechanism, but the product here will be OH right here, and you have this methyl right here. Okay, so if it's a primary carbon and secondary carbon, you will have the steric effect. The nucleophile will attack at the less sterically hindered carbon. So since goes really complicated, when you have this carbon, one carbon has tertiary carbon. So this is a tertiary carbon. It doesn't have any hydrogen on there. And then this is primary carbon. So in this case, the steric effect will not be the major effect. Instead, electronic effect will be the major effect. What does that mean? That means the radioselectivity changed here when there is a tertiary carbon. Why is that? Let's look at this example. If we have this, to start with, we introduce this acid as a catalyst. Okay. So we will have this intermediate. So at this moment, the reaction going on from here will be a reaction kind of between the SN1 and SN2 reaction. So the intermediate here, what we will see here is you do have the positive charge on this oxygen and kind of breaking this bond, but not fully breaking. So the leaving group is not fully leaves. And you will have partly positive charge on this carbon. At this moment, for example, you have the ethanol as a weak nucleophile. It comes in as a kind of attack this carbon right here. So this is the intermediate. And in this case, because this carbon here kind of the bond break here, so that kind of sort of form a partial positive charge at the tertiary carbon. It's kind of like a carbon cation, but not exactly yet. That is why it's more positive compared to this carbon. So it's more electrophilic. That's why the weak nucleophile actually will attack this more substituted carbon, the tertiary carbon. And that will give us our product here. Now this nucleophile will add to our tertiary carbon. Okay, and the last step. Okay, last step, you deprotonate hydrogen proton. Okay, that give us the final product. So we notice that is nucleophile is added at the tertiary carbon. So this is some complicated aspect of acid catalyst ring opening reaction of the epoxide that we need to think about regioselectivity at this moment. Now let's look at one example. If we start with this, again, kind of crazy looking epoxide. So now we have a tertiary and a secondary. Okay, so for this epoxide, if we introduce a strong nucleophile, then strong nucleophile always attacks the less sterically hindered carbon. So for this one, the product here will be the OET will be added to the carbon on the right, and OET, and that is steric center, so you will have the opposite inverted stereochemistry right on this carbon. Okay, right, because it comes in here, right, kick off this bond, so that bond goes down here. And if we start with this epoxide and we say HBr, then now what's going on here is you will have your Br added right here, kick off this part, and you will have your methyl SO, and then OH will be here, and you will have your SO group as it is. So in this case, what we are seeing here is acid catalyzed ring opening. We have the nucleophile added to a tertiary carbon, electronic effect ones. So this is the end of the video. I will see you all in class.